Hi everyone, welcome to the new video lecture series on binary multiplier design. In this video lecture series, we are going to cover different architectures to design a multiplier. And mostly we are going to cover three types of microarchitectures, which will cover both unsigned binary multiplication architecture as well as signed binary multiplication architecture. For signed binary multiplication architecture, we will be discussing the Booth's architecture. So now let's get started. So this is the simple principle of binary multiplication. I am very much clear that you all are familiar with this approach of binary multiplication, where we will be having two numbers, one is multiplicand and one is multiplier, and we will be multiplying each and every bit of multiplier with the multiplicand. So here the first bit of multiplier is 1, so 1 will get multiplied with multiplicand and it will result in 1 1. Then in the next step we will be basically shifting the partial product by 1 and we will multiply the next bit of multiplier with the multiplicand. So the next bit here is 0. 0 gets multiplied with 1 1 1 will result in 0 0 0. And in the next step we will again shift left the partial product by 1 bit and the next bit from the multiplier is 1. So 1 will get multiplied with multiplicand and it will result in 1 1. And finally we will add all these partial products and we will get the final product value, which is in this case 35. Now let's observe some important points here. So the first point is, if you carefully observe here, the partial products are nothing but either 0 or multiplicand. So this value is nothing but multiplicand, then this value is 0, this value is again nothing but multiplicand, right? So this is a very important point to design, which will help us to design the digital hardware for this multiplier. Point number 2. Point number 2 is, there are basically two operations which are taking place here. One operation is shifting and second operation is addition, right? So now let's see what is shifting here. The shifting operation is basically happening on the multiplicand. So here the multiplicand is 1 1, then here the partial product is 0 itself, and here again the partial product is 1 1 1, and which has been left shifted by 2 bit. Basically the multiplicand is shifting left. Okay, now we are basically adding all these partial products to get the final sum value, right? Now let's see what all do we need to design the hardware for this multiplier. So if you see, there are two operands, one is multiplicand and one is multiplier. So basically we need one register for multiplicand and second register for multiplier. To hold the values of multiplicand and multiplier, basically we need two registers, and let's call it a register M and let's call it a register Q. We will discuss the width of these registers later. First let's discuss what all do we need. Then next, what do we need? We need a variable to hold the partial product value, right? So let's call it a accumulator, where it will hold the partial product value, and finally after addition all the partial products, it will result in the final product value. Okay, so now let's discuss the width of these registers. So first of all, the product. So the product here for the 3-bit multiplicand and 3-bit multiplier, what will be the product? The product will be 6-bit. It is basically equal to 2 cross n. So the width of accumulator here is going to be 2n. Okay. Now the multiplier register, the width of multiplier register we will take equal to n. To hold this multiplier, we will need a register which width is equal to the multiplier number. So if the multiplier is 3-bit number, the width of the multiplier register Q is also going to be 3-bit. Okay, now let's discuss the width of the multiplicand. So if you see here, this multiplicand is basically, through these partial products, it is getting shifted left 1 by 1 for all the values of multipliers. So basically, if you see, the partial products are nothing but multiplicand. Okay, and the first partial product is nothing but equal to the multiplicand value, and then these partial products will be basically getting shifted. So here the multiplicand value is basically getting shifted left 1 by 1, right? So here we are going to take the width of this multiplicand register equal to 2n, the register which is M, and its width will be equal to 2n. So it will basically hold all the partial product values. I hope this point is clear. Now let's understand the flowchart. So as I said here, we are taking three registers. The first register is M, which will be a multiplicand register, we will call it, and it will be basically having the shifted value of multiplicand. And then we will have the multiplier register, which is n bit, and then we will have the final accumulator or sum, or you can call it a final product value, which is again going to be 2n. If you have the n bit multiplier, for example 16 bit multiplier, so the sum or the product value will be equal to 32 bit. Okay, so let's see how this flowchart will work. So after starting, what we are going to check? We are going to check the value of the LSB bit of Q, right? So if the LSB bit is 1, then what we are going to do? In the accumulator, we are going to store the sum values of accumulator plus multiplicand. So for example, in starting, when the multiplication starts, the accumulator basically will get initialized with all values as 0, 0, 0. And then if our LSB bit of multiplier is 1, then A will become A plus M. For example, the M is 5, or let's take it 101. So the A will become 0 plus 5. So A will, in binary, it will become 101. Okay. So here basically we will add the accumulator value with the multiplicand, and we will store that value back to the accumulator. Okay. Now if the Q0 bit is 0, if Q0 bit is 0, then we will not do anything. We will directly, what we will do, we will left shift multiplicand by 1 bit. So here if Q0 bit is 1, then we will add the multiplicand to the accumulator and then store the updated value back to the accumulator, and then we will shift the multiplicand by 1 bit left. Else if our Q0 is 0, then we will directly shift the multiplicand left by 1 bit. And next we will right shift the multiplier by 1 bit. Okay. So, and then we will check how many repetitions we have done. So here repetition means the addition plus shifting. So either there will be addition plus shifting, or there will be direct shifting depending on the value of Q0. So this operation is called one repetition. So we are doing these operations for all the bits of multiplier. So if the multiplier has 5 bits, then we have to do this operation for 5 times. Okay, so if we have not reached 32 repetitions, we will again go back and check the Q0 bit. Okay, now since the Q0 has right shifted by 1, so now the Q0 bit might here change or not. So again we will check for Q0. If this bit is 1, then we'll repeat the same procedure. We will add the multiplicand to the accumulator, and then we'll update the accumulator with the updated value. And then we will left shift the multiplicand by 1. Multiplicand here is nothing but the multiplicand register, which is equal to the width of 2n, right? And then we will also right shift the multiplier by 1 bit, and we will repeat this procedure until all the bits of the multiplier registers are not checked here. I hope this is clear. So this is the flowchart of a multiplier architecture. So this is one of the multiplier architecture. There can be another approach to design a multiplier, but here we are taking this approach. There might be another architectures where we need where these multiplications can be done with less number of flip-flops or less number of registers. We will explore these options as well in further architectures. Okay, now as I said, the algorithm or the steps of this algorithm are: first, clear the accumulator. So we will be basically initializing the accumulator with 0, 0. And here basically we will initialize the multiplicand register with the multiplicand value, and the multiplier register with the multiplier value. And then we are going to check the Q0. If Q0 is 1, we will add the content of multiplicand to the accumulator. And then we will do the logical shift, the content of M left by 1 position and content of Q right by 1 position. And we will check this, or basically we will repeat the step 2 and 3 for all the bits of multiplier, which is Q here. Okay, here is one example. So we have taken the example of multiplication of 7 into 7. So the binary values of 7 is 111. So what we will do here? So as we discussed, we need 3 registers. First is accumulator A. So in starting, accumulator is initialized with 6 zeros. So as we discussed, we need a multiplier with width 2n, then the multiplier Q register width n and the multiplicand M register with width of 2n, right? Then here in the first step, the accumulator is initialized with all the values zeros. The multiplicand register is initialized with the multiplicand value. These are the 3 bits and the rest of the bits are 0 0. And the multiplier register is initialized with value 1 1 1. And here the count is nothing but the number of bits in the multiplier, which is 3 here. Okay. Now in first step, we will check the LSB values of this multiplier, which is 1. So if the value is 1, then what we are going to do? We are going to add the multiplicand to the accumulator and going to store the value back to the accumulator, right? So here we have added the values of accumulator A and the multiplicand M, and the value which we have got out of this addition we have stored here in the accumulator back. Okay. Now in the next step, we have to basically left shift the multiplicand by 1. So here we have left shifted by 1, and we have to right shift the multiplier by 1. So here we have right shifted by 1, and since we have checked 1 bit, so our count will now decrease to 2. In the next step, again the Q0 bit is 1. Here if you see the Q0 bit is 1, so again we have to add this value and store the value back to this register accumulator A. And this is left shift of the multiplicand by 1 bit. Then we have the right shift of multiplier, and here we have again checked the second bit of the multiplier, so our count reduced to 2. In the next step, we have again added this value and this value, because our multiplier bit is again, it is going to be 1. So we have added this value, so our new value will become this, and we have here left shifted the multiplier by 1, and here we have right shifted it by 1, and our count becomes 0. So basically we have checked all the bits of Q0 here. So this is, and our count has become 0 here. So this is the final value here in the accumulator register is nothing but our product value, which is equal to 49, which is nothing but 7 multiplied by 7. So I hope all the steps of these algorithms are very much clear. So the few observations, as we discussed already, we need a multiplicand register with width of 2n here, and another important point is half of the multiplicand bits are always going to be 0. So you can see here, this is our multiplicand variable. Our multiplicand is basically a 3-bit value, which is 7, but the multiplicand register which we are going to take here to design the hardware is, we have to take a 6-bit multiplicand register, and in that 6-bit multiplicand registers, our half of the bits, that means 3 bits, are always going to be 0. Okay, so this is another point here which can be taken care for further optimization. And here we need a 2n bit sum or product register, and the time complexity in order of n square. That means if it is a 3-bit multiplier, we need 9 clock cycles to get the final result. We will also see this when we will go through the simulation of this multiplier. We will see how many cycles it takes before producing the final result. And we will optimize this algorithm, and we will come up with the next type of microarchitecture in our next video. So now let's work through the design and test bench code for this multiplier. So first we are going through the Verilog code of this multiplier. So here we have our multiplier module, which we have made parameterized. So here the multiplier, we can have the multiplier with different width. For example, 4-bit multiplier, 60-bit multiplier, or something. So now these are the global reset and clock signals. Here we have our input multiplicand, then multiplier. This is our input start for start condition. So whenever it is asserted, our multiplication operations will start. This is the final result, and once the multiplication is done, we are basically asserting this output underscore done signal for 1 clock cycle. These are the state definitions for this multiplier, and here we have internal variables. So as I said, so this is the variable to basically define these states, and here we have the multiplicand register. So if you see here, as we discussed, the width of this multiplicand register is basically 2n, and then we have our multiplier, which is nothing but n-bit multiplier. We have our accumulator again equal to 2n bit widths, and then we have our count register, which will basically count the number of bits in multiplier, for which basically we have to perform the addition and shifting operations. So on reset, all these registers are getting assigned to 0 0, or basically they are getting reset. And once we are out of reset, we will be in the multiply init stage, where we will be initializing these registers. And in init state, basically we will be waiting for the start input. So once we get our start input, we will go to the multiply load state, else we will be in the init state only, right? And in the load state, basically we will load our multiplicand register with the multiplicand value, which we will be receiving as an input, and our multiplier register with the multiplier value. Our count, the count will basically become the number of bits in our multiplier, which is n here, and our next state will be add. So here in add state, basically we are checking if our multiplier, if the LSB bit of our multiplier is 1. So if our LSB bit is 1, we will basically perform the addition operations, where we will add the multiplicand value with the accumulator, and we will store back the value to the accumulator register. And then we will basically shifting the we are basically going to the shift state. So in the shift state, basically if our count has reached to 1, so basically our count will start. For example, if we have 8-bit multiplier, then our count will start from 8 to 0. So when it will start from 8 to 0, then if we are starting from 8, then our all the 8 bits will be covered when we reach to 1. So when we reach to 1, when our count becomes 1, we are basically done. Our multiplication operation is basically done, and this done signal is asserted. Else we are keep on decrementing the counter by 1, and we will go back again to the addition state. And here our multiplicand registers, we will shift the multiplicand register by left shift by 1 bit, and our multiplier register right by 1 bit. And once the multiplication operation is done, once we are in the done state, from done state we will go back to our initialization state. And these are the output ports. So our register done value will get assigned to our output done value, and once we are done, then our accumulator value is basically nothing but the final product value, which will get assigned to output result, else it is 0. So once done is asserted, that particular cycle, our accumulator register value will be assigned to the output port. So I hope this Verilog code is very much clear to you. Now let's synthesize this code. So to synthesize this code, we will be selecting the Yoshi synthesis tool here, and we will check the show diagram after run. We will save this and we will run it. Okay, so here is the Yoshi synthesis diagram which has been generated. So you can go through each and every components of this diagram which has been generated by Yoshi synthesis tool to understand the synthesized diagram of this multiplier. So you can see here that we have our reset signal, then this is our clock signal and our start signal. So how this start signal is basically going, and it is basically controlling the state machine of our multiplier. So this is a big diagram here. You can go through it and you can understand the components of this diagram, the digital components of this diagram one by one. Okay, now let's go through the test bench of this multiplier and let's simulate this design. So this is our multiplier test bench. Here we have the parameter which will basically define the type of our multiplier, whether it is a 3-bit multiplier or 8-bit multiplier. Here we have the input output ports of our design. Then we have the DUT instantiation here. Here we have a clock signal generated of 10 nanosecond time period, and then we are basically initializing the signals, and then we are basically here giving the inputs to our DUT, where the multiplicand value is 7 and the multiplier value is also 7. And here we are observing when we get our done value, when we get a positive edge of done. So the done is asserted by the multiplier hardware whenever the multiplication is complete. So whenever done is started, we are basically making our start signal 0, and we are displaying the result also here. Okay, so this is the piece of code to basically dump the signals to the waveform window. Okay, now let's simulate this. So to simulating this design, we will use the Aldec Riviera simulator. We will here enable this open EPWave after run. We will save this design and we will run it here. So we are also using some display statements to display the output. So let's first see the what it has displayed. So if you see here, here it has displayed that the product value is 31 when done value is 1. So product value 31 means nothing but in decimal it is 49. So the multiplication of 7 cross 7 is nothing but 49 in decimal, and in hexadecimal we are basically printing in hexadecimal, so it is 31. Okay. Now let's see in the waveforms. So let me check it in the binary here. So you can see here that this start is asserted here, and the multiplicand and the multiplier registers are basically getting initialized here with 111 and if you see here the done is going high here. So once the done is going high, then whatever the value of accumulator is will be displayed on this output result port of our multiplier, right? So here the value is 11001, which is nothing but decimal. In the hexadecimal it is 31, or in decimal it is 49. So now let's see how many cycle it has taken before producing the result. So you can see here our basically initialization started here. So after this initialization we have taken 1, 2, 3, 4, 5, 6 or 7 cycles. So it is basically more than 2n and less than n square. So generally the complexity of the bit complexity of this general multiplier is in order of n square. So I hope this multiplier architecture is very much clear to you. If you have any doubts, please write down in the comment section. Also, if you like this video, please hit the like button and do subscribe this channel and press the bell icon so that you will get notified as soon as I upload the next video on this series. Thank you very much.